overview about what we're going to talk about. We're going to start with cloud computing, then Cloudlets for computing and MEC, and finally we're going to go through the research directions. So tonight we're going to barely touch these topics. There are a lot of topics, and for sure we cannot cover all of them in detail. So please feel free to interrupt me at any time, and if you have any question or any comment. So let's imagine that everything is okay. Our situation, no restriction for travel, no health concerns, and you wanna travel somewhere after this long self-isolation because of this health situation that currently we have. So just think about what is the possibilities for you to buy a private jet for that travel. Actually, I believe that the chances that you think of buying an airplane for your trip is very low. Instead, I think you will rent one or a few seats depending on your need on this specific route. So with this example in mind, let's move to our topic, which is the cloud computing. Cloud computing is all about delivering on-demand computing services. So instead of purchasing and installing, running a software application locally by a user, he or she uses an application that that a cloud provider owns and maintains. And since the location of that service is largely irrelevant to the end user, the term cloud has been used to describe this technology. And if we think about computing as a service, actually it's not a new technology. Computing as a service has been existed for a while, since 1960s. Companies back at that time, instead of buying an expensive computing mainframe, they used to rent time on that mainframe to do the computation. The Google CEO first proposed the concept of cloud computing on Search Engine Strategies Conference on 2006. And since that time, a lot of big companies started to use the cloud computing technology. Amazon, IBM, Google, each of them, and a lot of other companies, and even the e-commerce companies like Alibaba on 2009 started to establish the first e-commerce cloud computing center. If we talk about the services, there are three main services in cloud computing: either software as a service, platform as a service, or infrastructure as a service. And the difference between these three main services is is the control of the user over those different layers. So as you can see here, like the orange layers indicates the layers or the things that the cloud provider controls, and not you as a renter or as a user of those services. And as you can see in software as a service, let's say company, university use software as a service, so it has no control over everything, just use that software. In platform, there is a bit of managing and control. As you can see, the blue rectangles here on application and data, and in infrastructure as a service, there is a bit more control, which is like different OS, different operating systems, middlewares, and so on. And a company can have its own private cloud. So on-premises means that there is private cloud owned by a company. So in this case, if we talk about cloud computing types, there are three main types of cloud computing. Either there is public cloud computing, which is owned and controlled by a third party, and people tend you use or rent those computing powers, or private or on-premises cloud computing, or a hybrid of private and public cloud computing. So when we think like it's really perfect to have strong computing machines. So if we have a camera, for example, it's perfect to have a strong machine to do the computation, to analysis those data. And then when we think about cloud computing as a technology, it's really perfect to have those strong machines to do those heavy computation instead of normal machines. But when we think about it, everything has to be sent there. So there is a traditional problem of centralization. So the traditional cloud computing centralization, like processing on cloud, do the storage on the cloud, these kind of things may lead to some limitations, which we're going to see in a moment. A lot of like big companies like Google, like Amazon, like for example, IBM, they have their own cloud data centers. So they are centralized units which reside somewhere in a different regions and continents to do those computation on behalf of other weaker machines. So when we think about IoT devices, and tonight we're not going to talk about IoT, but I think almost all of us like are familiar with term of Internet of Things, which are like billions of devices or things that are connected to each other. So when we think about those billions of sensors, we generate a lot of data. So those big data, which has been generated by those sensors, cannot transfer and process in the cloud in a centralized unit. A lot of issues like latency, bandwidth, security, or privacy can be happen here. When we think about latency, there is a large average of separation between a mobile device, which is literally on the edge of the network, and a cloud, which is on the other edge of this paradigm. And this end-to-end communication involves many network hubs, and this results in high latencies, especially when we are talking about like very sensitive applications. Sensitive, I mean, in terms of latency, in terms of computation, for example, face recognition, object recognition, augmented reality. So there is a big problem of latency. And for example, in autonomous driving, the maximum allowed latency is 50 milliseconds. And in smart grid, it's even worse, 20 milliseconds. And when we think about the average round trip time of Amazon cloud server, which is 74 milliseconds, for sure here we have a big issue of doing those computation purely on the cloud. So this is just one side of the problem. Then with term of bandwidth, the current autonomous, like it's calculate that the autonomous driving, an autonomous vehicle, a single autonomous vehicle generates up to 4 terabytes of data per day, which is like a huge amount of data which is generated. In terms of smart meters, only in United States per year, 53.6 petabytes of data will be generated. And recently, a few years ago, when IoT enters the aircraft industry, a GTF engine, which has up to 5,000 sensors, it generates 10 gigabytes of data per second. So a twin engine aircraft of a single flight, which is like a normal and average of 12 hours, it will produces up to 844 terabytes of data per flight, per airplane. Then in terms of storage location, some legal implications may raise when some sensitive data are collected in one country from some IoT devices, and they are transmitted to the cloud data centers in another country, which may have different regulations regarding dealing with those data. And when we are talking about GDPR, for example, in Europe, there is a very big issue, even now, like in terms of online learning. Then, if we talk about transferring all those data to the cloud, mostly those data are resource constrained objects, which means that even some of them, they cannot do public key encryption. So we know that to protect those transferred data to the cloud, we have to use encryption. And some of those IoT objects may not even have enough resources to do encryption and encryption, for example, RSA, which is like based on public key encryption. If you want to achieve some required security services, we have to think about this issue. So in addition, there is another issue that by sending those data to the cloud, we simply put our trust on the cloud provider. In the example that we have started with, that the flight, basically when we choose a flight, we put our trust on on that airline or on the pilot, which I would say it's not always the best thing to do. So a lot of scientists thought about those issues and proposed some different computing paradigm than just this cloud paradigm, which, for example, today we're going to talk about cloudlets, mobile edge computing, Furtwangen edge computing. What are their fundamentals and the relationships? So let's start with cloudlets. Cloudlets proposed by a professor in University of CM in USA, Professor Satya, as he likes to be called, in 2009. So cloudlets, basically, they are small-scale data centers. They are small cloud, which are like basically inexpensive and maintenance-free devices that are located at the edge of the internet, somewhere close to the end devices. Then an experiment done to measure the differences between having those cloudlets or using only the IoT devices and the clouds, like the differences between these two paradigms. And during the evaluation, Amazon Web Services has been used. Amazon Web Services, basically, there are on-demand cloud computing platforms. There are APIs that provided to individuals, companies, and governments on a meter pay-as-you-go basis. I know a lot of scientists, postgraduate students, they use the free version of Amazon servers to do the simulation instead of doing that locally, for example, in your PC. There are some regions in Amazon Web Services, in cloud servers. The first one is, they used 4 out of a lot of regions that the Amazon has. The West US, so basically US, but in West part of US. So the East part of US, the US East, which the university resides there. Then the EU region and the Asia region. So they used, first example that they used was the augmented reality. As you can see here, there is a big difference and in terms of efficiency of using a cloudlets for augmented reality to compare, for example, to using the cloud. And as you can see here, I don't know whether you can see or not, but I hope that you can read the numbers here. You can just think about the cloud computing. Do the augmented reality in the mobile itself requires less energy and less time than the cloud computing in Europe or in Asia, or even in the cloud of the United States itself, but in the region of West. So 3.3 compared to 5.1, and even in terms of time, there is like closeness between those clouds and mobile only. So here, as all of us can see, like the best one in terms of efficiency is the cloudlets. So they did another experiments in face recognition, and what they did is, very sorry, I have a technical issue. Yep, it's solved. So in terms of face recognition, they basically what they did, they either did the computation on the mobile itself, and like this study is a few years ago, or send the image from the device itself over Wi-Fi first hop to the cloudlet or to the Amazon Web Services somewhere in Europe or in the United States. So as you can see here, there is again a big difference in terms of efficiency of those two paradigms, using cloudlets or using the clouds. And back at that time, like the computation, as you can see, none of them could do the face recognition within first 1 minute, because it took 4 minutes for like 2 minutes for some of them. And for the cloud in Asia, it took almost 4 minutes to do the computation. So imagine that you have a mobile and you are using a cloud service, and by chance right now you are connected to a different region that the preferred one. So it takes almost 4 seconds to do the face recognition. Then, so this is actually the main issue that we can think about in terms of cloud. So there is a big difference in distance between those devices. If we are talking about the end devices, or even if we are talking about the cloudlets. So the cloudlets itself, adding the cloudlets to the system, it solves part of the problem, but as you can see, there is still a big issue here of having those computation. And so you don't have to even talk about cloud computing. It takes a few seconds to talk even about the cloud computing, doing the face recognition there. So let's continue with the issue here. So it's obvious that deployment of IoT applications in a two-tiered way, and what I mean by the two-tiered way is like the cloud and the IoT devices itself. So the things and the cloud. So the IoT devices here, they required low latency. They had a lot of, they had high mobility. So a lot of issues with that. So if you wanna summarize the problem, it's almost about centralization. Then, while we saw that using a three-tier architecture of the things, cloudlet, and the cloud could solve some of the problem comparing to the cloud computing itself, but since the computation still is done in cloudlets and later on in the cloud, so there is still a requirement to do a lot of improvement in terms of time and efficiency. Simply, the solution that scientists thought about is to use a multi-tiered architecture, at least the three-tiered, which they called it for computing. And we're gonna see in a moment what does it mean, and even why they decided to use fog as a term for that. So the three-tier computing, they added another layer between cloud computing and between IoT devices, which is the fog nodes, or what we call the DABAB. So the main idea here is that extending the cloud, instead of doing the computation there, extending the cloud to be at the edge of the enterprise network. Then what we called it the fog. So it consists of network-connected computing and storage devices, for example, controllers, routers, and so on. And basically, the fog layer tries to perform the pre-processing in the fog layer itself and do the more expensive computing and storage stuff in the cloud. So it tries to keep the data as close as possible to the origin of those data. So here we are talking about billions of nodes, vehicles, IoT devices, and so on. And the fog layer tries to keep the data as much as possible, as close as possible to the IoT devices itself. And the reason behind choosing fog as a name, because fog in term, it means like the cloud, which is a bit closer to the ground. So when we talk about fog nodes, there are different fog nodes. Then core network routers could be a fog node. Then any advanced switches, gateways, Wi-Fi access points, even cellular base stations could be a fog node, and resource-rich end devices like vehicles, for example. So we're gonna see in a moment that for each of those, actually I just talked about cellular base stations and end devices, there are some subsets of fog computing. For example, if you put all the intelligence in the cellular base stations, here a specific subset of fog computing, which we call the mobile edge computing, and so on. Even so, when we talk about vehicles, we all are familiar with, or at least know about the 5G. So although the 5G will make the wireless communication much more efficient and powerful, but they will still being unable to handle the demand of world's autonomous cars. We are talking about huge amount of data, as we saw, like 4 terabyte per autonomous vehicle per day. And so there is a requirement or a need to do to a car, for example, an autonomous car itself, to be able to compute and make decisions based on the data that it gathers or it generates locally. Then, before moving on to the concept of edge computing, which is a lot overlapped with fog computing, let's just talk quickly about content delivery network. So this is not a new concept. It is not a new technology. It has been for a while, like since late 1990s, which back at that time there were very let's say poor internet connection. So it tries to mitigate the performance bottlenecks of the internet. The CDN uses nodes at the edge, which are a bit close to the users to prefetch and cache the web content. So it works like the content owners pay to the CDNs, and in order to handle those high quality, or let's say quick services to the end users, then the CDNs pay to the ISPs, to the internet service providers, and to the network operators for hosting its services in their data centers. So in this case, if we are talking about like back at 1990s, then a video sharing back at that time, which still like needs a high bandwidth, so it could be performed in a best possible way. And even when we are talking about the location where advertisement could be done back at that time. So by having that in mind, the content delivery network and the concept behind moving or pushing the services close to the edge or to the end users, now let's introduce or talk about the edge devices or the edge computing. Edge computing, as part of fog computing, moves the computation to the IoT devices themselves or to the directly connected gateway. So basically, edge computing generalizes the concept of CDN that we just saw, and it tries to leveraging the cloud computing infrastructure within these concepts to having the required efficiency that we are looking for. In terms of fog services, the fog services may be anywhere between the cloud and between the edge devices. And those fog services hosted in what's so-called fog nodes, as we talked about what could be a fog node. Then there are a lot of definitions. Actually, there is no consensus about what the fog computing can be. There is no one single definition of fog computing, or even one strict and clear definition or about what is the difference or the overlapped area of fog and edge computing. But one of the nice definition that I prefer, which done by Cisco, is that fog computing is a standard that defines the way that edge computing should work. So basically, it manages the relationship between the end devices and between the cloud data centers. So by having that in mind, let's move to the multi-access edge computing, which is again another subset of fog computing. So IBM's and Nokia, they had already installed and working network, and we are talking about the GSM network, the telecommunication network. So they introduced the first computing platform that could run applications and services directly within a mobile base station. And when we think about the mobile base station, basically this is the edge of the telecommunication network. So they put the intelligence inside the edge of their network by having a MEC server, a multi-access or mobile edge computing server there doing the computation. And basically there is usually just one hub between the end user, which is the mobile user, and the base station that is connected to. Then the European Telecommunication Standard Institute, basically they standardize this technique, this concept, the IT service environment and the cloud computing capacities in the base station specifically, and they created the concept of mobile edge computing, which later on they renamed that to multi-access edge computing. So before moving on to the research directions, to some like challenges, the ideas behind that, let's talk briefly about all the techniques that we already mentioned. So there is Cloudlet, mobile edge computing, fog computing. What are the differences? What do they mean generally? The Cloudlet simply is a small data centers, a small cloud data centers, which is a bit closer to the edge of the network comparing to the cloud itself. So talking about mobile edge computing or multi-access edge computing, MEC here shares the same idea that Cloudlet has by creates the MEC servers in the edge of the telecommunication network. And when we are talking about telecommunication network, GSM network, the edge of that network basically is the base station. Then both of them, they are part of edge computing. And what edge computing does, it tries to move the computation to the IoT devices themselves or to the directly connected gateways. And nowadays we have, like with only €5, you can have already worked Linux system, which is the Raspberry. And you can use that for to bring the intelligence to the device. For example, we talked about camera at the beginning of the talk. That we said, for example, camera back at that time with cloud computing, all it does is to send the data to the cloud. So this is a totally dumb camera with no intelligence. So by adding this €5 Raspberry, for example, which is a Linux or any microcontroller, we can turn it into an intelligent device and do the computation, at least part of the computation there, and not all of that in the cloud. So for computing generally creates a layer between cloud computing and the end devices. And it tries to manage the relationship between them. And the most important thing that you have to keep in mind, let's say the take-home message, but we are right now in home, so the stay-home message here is that the main idea behind fog computing is to distribute the computation close to the end users. So the fog computing tries to keep the data as close as possible to the origin of that data and distribute the computation in a lot of devices instead of relying on a centralized cloud in terms of cloud computing. So although there are some differences between fog computing, between mobile edge computing, between cloudlets, but simply they share a similar vision. They want to extend the cloud and brings it closer to the end devices. Then before moving on to the research directions, let's ask, when we have to use fog computing, probably is a very important question, that when we have to think about use fog computing and not cloud computing, what are the signs that indicates that we have to move to the fog computing? First of all, if the data is collected at the extreme edge, for example, we are talking about vehicles, so it's the extreme edge of the network. And if there are thousands or millions of things at a specific area, we are talking, for example, about a company, or about a single engine in the airplane, so there are 5,000 sensors there. And it's not logic at all to send all those data and use the pure cloud computing. And if we need less than a second to do the analysis and to do the computation, in this case, we have to keep in mind of using fog computing. So moving on to the last part and probably the most interesting part, which is the research direction. So here, just keep in mind, I know that we are from a different background. Some of us like working on multimedia, on AI, on data mining, and so on. So please take the parts that are like, let's say, useful or fruitful for you within this topic. Because right now in research directions, I try to touch barely all the topics that are available in terms of fog computing. First of all, let's talk about MEC Research Directions. We talked about mobile edge computing, and we know that mobile edge computing is a specific fog computing paradigm that put the intelligence in the base stations itself and nowhere else. So we will talk about MEC, then we will move forward to the fog computing, which is the general set here. And you will see some similarities for sure, because basically we are talking about a subset or a specific type of fog computing. First of all, in deployment of MEC systems, there is no formal definition of what is a MEC server and what a MEC server should be. And the location of those servers in the system are not specifically specified, whether they have to be on the base station itself or close to the base station and so on. So one of the main research directions here is the deployment of MEC systems. For example, the site selection for the MEC servers, and for example, the network architecture as well. Then when we are talking about mobile applications, for example, we talked about video streaming. When you talk about video streaming, there are some video streaming there are some content that they are popular and could be repeatedly requested. So one possible solution here is to avoid the frequent replication of those data of the same content and to use caching in base stations. Again, here is a lot of research done in this field. And here specifically, we are talking about mobile edge computing. Then we are talking about mobile devices for sure. So the end devices here are the mobile devices. And as the name says, mobility here is a significant challenge. So here, topics such as mobility-aware fault tolerance MEC or mobility-aware server scheduling can be studied in this field in terms of mobile end devices. Then we talked about cloudlets or about MEC servers, and for sure those MEC servers, they consume less energy than the cloud data centers. But here we are talking about not just a single MEC server. We are talking about, for example, let's imagine a dense deployment of that scenario, which raises a big concern of the system-wide energy consumption. So here again, there is a big challenge in terms of in terms of power, of the used power of those data centers, especially when we are talking about designing a green MEC systems. Then the very important part of almost every system is the security and privacy issues in MEC. Since we are talking about mobile devices, and those devices can be, for example, if you are traveling in the system, in a city, in the same citrate, you could do what's so-called offloading to connect to a different cell, different base station. So only this scenario, a lot of issues could happen, like trust, authentication mechanism, networking security, secure and private computation that we need in this term. Then move on to a wider area, which is the fog computing. In terms of foundation, there is still a lack of standards, of theoretical modeling, of performance metrics that the fog computing architecture used. Another field of study in fog computing is the frameworks and programming models. For example, the general architecture for the fog computing. Then if we talk about architectural model of combining, for example, the MEC and the fog computing in the 5G networks, a very recent topic. Or, for example, fog architectures in 5G and, let's say, in Internet of Vehicles, just an examples of those things. Again, in resource model, there is a lot of issues. For example, answering to the question that the fog services, we are talking about fog resources. So a question may raise that what is the party that has to provide those resources? Whether the fog server providers have to provide all those fog resources, or a simple end user can bring, let's say, their devices and share their resources there. Then in terms of design and planning, for example, design a framework for Cloudlet-based network design, planning, answer again to the questions that that the data centers, we are talking about the edge data centers, where exactly those data centers has to be, and the computation capacity that are required, that needs from those data centers. Then in terms of resource and energy estimation, for example, we want to design a model that analyzes the required fog resources for any use cases, for any offered IoT workload. Just something keep in mind here, that when we are talking about resource, we are talking about two different resources, about fog resources and about IoT resources. So IoT resources are those which reside in the IoT layer, in the end layer, in the edge layer. And fog resources are those resources which reside in the fog layer, in the fog, which also called fog nodes or resources. Then there is, in terms of resource management and provisioning, placement of virtual machines, placement of services, the control and monitoring of those resources, the fog resources, or the discovery of resources, whether they are IoT resources or whether they are fog resources. And I'm gonna give an example, just bear with me, keep in mind about the resource management. I will give an example in a moment about the resource management in fog computing. Then in terms of application, some of you which are like from a different background, let's say in healthcare, a lot of applications in fog computing and healthcare, bandwidth saving, video and game analytics, then image and face recognition in fog computing. It's a very, let's say, very hot field of study for researchers, and artificial intelligence, machine learning here, a lot of similar issues in applications. Then in terms of software and tools, some simulators and emulators for the fog nodes, or the edge computing middlewares, designing the edge-based data analytics, and most importantly, distributed deep learning. Then same thing with hardware and protocol stacks, and finally with security and privacy. I'm gonna come in a moment to the security and privacy and talk a bit in detail about security and privacy. So let's talk about an example of resource management, then move to the security and privacy in fog node, which is the last part of tonight's talk. An example that we did is the distributed resource discovery. So we used a peer-to-peer scheme in fog nodes to create basically an overlay, a peer-to-peer overlay, and we designed the 3 versions, which has been presented in different events in London, in Barcelona, and in Lausanne, of using this model with different ways of creating private layer of resources. So here, everything is distributed. There is no centralized computation. and there are some security requirements that has been proved and that have been proved and achieved. For example, creating private layer of resources which cannot be discovered by all by all nodes, or attribute-based clients. So allow the clients to discover resources based on their attributes. For example, just the students in the University of Al-Qadisiyah, they can access the temperature sensor, whatever resource is there, or any other resource inside the university, so that no one else can discover those resources. And we use some cryptographic primitives and protocols for that. Then moving on to the last part, which is the security threats in fog. There are four main points, weak points, or let's say main points that the system can be attacked. Either the network infrastructure, or the core infrastructure, which is the cloud, fog infrastructure, or the end devices or the edge devices. So let's start briefly about the network infrastructure. First of all, denial of service, but because we are talking about distributed architecture, this attack has a very limited scope. Then man-in-the-middle attack, this attack is really dangerous, as it can affect all the information traversing that particular node that the man-in-the-middle attack is done to. Then the rogue gateway is its effect, actually its impact is similar to the man-in-the-middle attack, so there is a malicious gateway. Then when we're talking about the cloud, so the privacy leakage, which is information that resides here, this information can be accessed by an unauthorized entity. But because we are talking about the fog computing, some of those that are managed in lower layers, let's say in edge layers, in fog layers, and so on, then again, so this privacy leakage can be limited, especially comparing to the cloud computing. Then same thing with service manipulation, which adversary manipulates the information flow. And in this case, again, because of the distributed nature of the whole ecosystem, so this kind of attack might not affect the whole system. Then with rogue infrastructure, it's mostly impractical, but extremely dangerous if it happens. So it is, again, another point of study. Then with fog infrastructure physical damage, we are talking about some devices which are physically installed in public, so they can be attacked from there. Then same thing with privacy leakage that we talked in cloud layer. Then here, for example, some internal adversaries access the information flow that traverses that edge, the fog node. Then privilege escalation, which can happen by incorrect maintenance or misconfiguration, and service manipulation, again, by doing the privilege escalation, for example, selective denial of service, and finally, the fog node. Then here is very dangerous scenario, especially if we are talking about a fog node which hundreds or thousands of objects or IoT devices they rely on that node. In this case, it could be a very dangerous scenario. Then there is a trust model usually you can find with a lot of papers. So basically you have to put your trust, what's so-called trust anchor, somewhere in the network. So last part is about end devices, and we're almost done. When we are talking about end devices, a lot of them has no, as we talked, a lot of them cannot do heavy computation, or even they have no enough resource. So there is a specific field in cryptography with what's so-called lightweight cryptography, created lightweight symmetric and asymmetric encryption and decryption algorithms for those devices. So you can see the term of resource efficient cryptography, even in AES encryption, which is considered a bit, let's say, efficient, especially comparing to public key encryption. Still, you can find a lot of light version of AES encryption like present and so on. Then about location privacy, which is super important if you are talking about private resources, data privacy, and service manipulation, which is, for example, a device which participate with some other devices to do some malicious, to provide some malicious services, and finally, the injection of information. So in injection of information, we are talking about provided information by some nodes. Let's say a temperature sensor somewhere reside in a public building. So again, data validity here is a big concern of those devices, those provided devices. You ask for something, a resource about something, then you have to be sure that this is a valid data. So finally, I'm talking briefly about the data validation network that we proposed. Then the data validation network ensures that the generated data by those data sources are trustworthy. Then it uses the unused computation power. For example, let's say unused computers in a shop or rarely used servers. All those devices will be used here in the data validation network. Then all of them, they calculate the data quality value, and this data quality value can be normal or anomalous. Then for the data quality computation itself, a simple thresholding or machine learning can be used to do those computation. Then these validation are distributed, and since these are distributed, then we have somehow resistant against some known attacks that has been studied, because in this approach, it guarantees that these data validators are selected uniformly at random with a distribute computation. So it provides some security requirements that we already proved. Thank you so much for your listening, and you are welcome to do